So I will briefly conclude the topic of PageRank. Then I will briefly explain another ranking technique called hits. And then before starting the following lesson, I will spend 5 minutes to tell you what my lab does and what you can download from our website. I think this is interesting for you. Okay, so let me start with, okay, like this. Yeah. Blah, 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 blah. So yesterday we spoke about PageRank. Let me briefly recapture what we said, because we said a lot of different things. And well, some of them you got, some of them you should read again on the slides that I gave you. But the point that is interesting for me is the following. Okay, is the following. So PageRank is a ranking technique based on links. So basically, it is a way to determine, given a directed graph, which nodes are more important. So in a sense, is a way to determine centrality. I know that Sebastian spoke about centrality, right, in his lectures. I don't have time here to face the problem overall. This is actually something very interesting. So in general, the problem is I give you a graph that represents relations among objects or among individuals, and you want to tell me which individual is more important. Actually, there are many ways, many ways. There are many measures that are called, in general, they are called centrality measures, and they were not invented by mathematicians or by computer scientists. They were invented by sociologists, starting from the 50s. There is a plethora, there is a big number of measures of this kind, like betweenness, closeness, Katz index, many. PageRank is one of them. You can think of PageRank as a measure of centrality or a measure of importance, but it's not the only one. And what's important to know is that PageRank not only depends on the graph, but also on some other things. And all the class of yesterday was about these things. It was about how to choose the damping factor and whether choosing different damping factors can affect PageRank. The answer is yes. And also the two other things, the two other ingredients that you need to set before computing PageRank, that is the preference vector and the dangling node distribution. In particular, I did not tell you what the preference vector is about. So the preference vector actually is used in the literature about PageRank to bias the PageRank towards some pages. So if you don't know anything about the user that is going to submit the query, you probably are going to set the preference vector as the uniform vector. So 1 over n for every page. But suppose that I know already that the user that is submitting the query is more interested in pages about sport than in pages about, let's say, gossip. Then I will choose a preference vector that gives more importance to pages about sports than to pages about gossip. So the preference vector is a way to choose the bias of the user that is submitting the query. And Google can do that because when you if you have a Google account, as you probably have, Google may use what he knows about you to bias the interest on pages. Are you following me? So this is the way, this is the reason why V exists. V, the preference vector, can be used to bias the starting preference of the users. Because remember what V is about. You have this random surfer that surfs around the web, usually following out links. But from time to time, it teleports. It's like a user that keeps clicking, like a monkey, keeps clicking on links, and at some point, he gets bored. Now, if you don't know anything, when he gets bored, he jumps to a page at random. But if you know the user, you know that if he gets bored, he will jump to a porn page, for example. So he will give more preferences to some pages than to some other pages. This is where he lands when he decides to teleport. Okay? So PageRank is a form of link-based method to establish page importance. There are other examples, and one of them is hits. Hits was invented by John Kleinberg. John Kleinberg, by the way, do you know the name? Have you ever heard the name? So John Kleinberg is, I think, one of the most important scientists that is working on these subjects today. And he invented hits more or less in the same span of years as PageRank. The idea of hits is interesting because it doesn't assign a single score to every page, but actually it assigns two different scores to pages. So PageRank gives one score to every page. Hits gives two scores for every page. And the reason is the following. There are pages that are authoritative. Authoritative means that they are interesting. And there are pages that are hubs. Hubs are not pages that are interesting per se, but that they point to many interesting pages. So actually you can have two different scores for every page. One tells you how authoritative a page is, and one tells you how hub a page is. Okay? So clearly there is a dual relation among these two notions, because a page is authoritative if it's pointed by many hubs. And the page is a hub if it points to many authoritative pages. You following me? So we will have actually two sets of equations that are mutual recursive. And one computes the authoritativeness score based on the hubbiness score of the pages that point to the page you're interested in. And one will measure the hubbiness score of a page based on the authoritativeness of the pages it points to. Actually, differently from PageRank, hits was defined to be query dependent in the following sense. So here you must be very careful, because hits is partially query dependent in the following sense. You start with a web graph and with the query that the user submitted, and you do a sort of preselection. The preselection serves to reduce the size of the graph and to concentrate on a smaller graph that will be a subgraph of the original web graph. And then on this subgraph you compute hits. So the query dependentness is only in the first part, in the selection. Then once you have selected the graph, the subgraph, hits is a simple computation on the subgraph itself. So it's partially query dependent in the sense that, as it was defined, the query serves to select the pages. So actually the hits algorithm works in two phases. The first phase, given a query, selects a certain graph that I will call GQ that depends on the query. So for example, if your query is pizza mozzarella, then it will choose in the whole graph a set of pages that are related, in a sense, I will be more precise about it later, to this notion, so to pizza mozzarella. This way you will have a subset of pages with the links between them. And then at this point, for only those pages, you will compute the authoritativeness and hubbiness score. And at the end, you will use the authoritativeness score to score the pages. Okay? So let me be more precise about how phase one works. So you have this query, pizza mozzarella, and you select the pages. So the pages are selected as follows. First of all, you use some text-based technique to select the pages that contain the word pizza and mozzarella. You can do it either in a very stupid and binary way, like selecting only the pages that contain the two words, or you can be more smart. For example, there are techniques, I'm not going to tell you about these techniques here, but there are many information retrieval techniques that do a very good job in trying to match a query, a textual query, with the text of a page. One of the most popular is called BM25. Is anybody aware of what BM25 is? So it's a formula. You can look for it in the web. It's a big formula that, given a query and given the text of a page, it will compute a score that will try to tell you how likely it is that the page matches the query. And it's based on the number of occurrences of the query words in the page, on the overall number of occurrences of the words in the collection, blah, blah, blah. It's a formula. So at the end, with this formula, you will have, for every page, a score that tells you how likely it is that the text of the page corresponds to the query. And then, from this score, you select the top K pages. So you select, I don't know, the 1,000 pages that, based on the text, will most likely match your query. And then after that, you do the following. For each of these pages, you also add all the nodes that are pointed by these pages. So I selected, let me draw because it's easier. Oops, no more paper. Okay, so this is the big web graph. This is the set of pages that match the query in a binary sense, or the top K pages that match the query. Then for each of these pages will point to some other page. Some of them will be in the set already, but some of them will be outside. I take all those pages, the outgoing arcs. And then each of these pages is also pointed by many pages. So ideally, you would like to select also these incoming pages, but there are too many of them. So instead of selecting all of them, for each page, you select uniformly at random each of its in-neighbors, and you put them in the set. This is because the number of incoming links can be much larger than the number of outgoing links. Why? Because the outgoing links are the links that you did put yourself manually in the page. So you don't want to put too many anchors in your page, because you have to write too much HTML. But then the links, the incoming links, are pages that point to you, and that can be millions of pages if you are popular. So that's why. So this is how the graph GQ is built. And then once you have built the graph GQ, as I told you, you have to compute two scores. So for every page X, there are two scores called H of X and A of X. H of X is the score of hubbiness, and A of X is the score of authority or authoritativeness. You compute them iteratively. So at every time t, you will have a hubbiness score and then authoritativeness score. At time 0, all the pages have the same score, which is 1 over n. And then to compute the score at time t plus 1, you do the following. So how authoritative is page X? Well, it depends on the pages it points to. So you look at the pages X points to, and for each of these pages, you sum up its authoritativeness. Because a page is a good hub if it points to authoritative pages. And on the other hand, a page is authoritative if it's pointed by many hub pages. Okay? So that's what you do at every step. And actually, as you see here, I didn't write equal, but I wrote proportional to, because you have to renormalize those scores. So at every step, you renormalize the scores so that they sum up to 1. And well, this process converges and blah, 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 and you get a result. And actually, what you're interested in is only the authoritativeness score. But the other one is necessary to compute this, because they are mutual reinforcing scores. So this is how hits works. Now, as I told you, in the way Kleinbergs define the hits is based on a subgraph. But in theory, in principle, you can apply hits even on the full graph. It will tell you something. Will it tell you something? Well, actually, you can use it as another measure of centrality. And I have a paper that I'm writing, actually, that tells you that hits used on the full graph doesn't mean almost anything. It means almost nothing. So it works much worse than PageRank. And there are reasons for this, but I don't want to enter into these details now. So is hits used somewhere? So do search engines use hits? Apparently not. Because it is dynamic, first of all. So differently from PageRank, you must compute it after the user submits the query, which means that it's very computationally intensive. And its benefits over PageRank are really marginal. Even on the subgraph, its efficiency is really marginal. It was supposedly used by a search engine that now doesn't exist anymore, that was called Teoma. Later it was called Ask, and now it's called nothing because it doesn't exist anymore. Actually, we don't know. Every time I speak about search engines, I should say that I really don't know if there is a search engine in the world that is using hits. At the best of our knowledge, there isn't, but maybe there is. So, okay, this ends the first part of my course about ranking techniques based on links. You have any questions? Did you get my assignments, by the way? Did I give you my assignments? Yes. Okay. Good. So, before proceeding with the following, before proceeding with the following part, I would like to show you the homepage of our lab. So our lab is called the LAW, like Law and Order, LAW, which means Laboratory for Algorithmics of the Web. And you can Google for it, and this is us. Now, here on this website, you find many things like blah, blah, publications, but the two things that you're probably more interested in are software and datasets. So let me start from the datasets. We distribute a number of datasets that you can see here. So all of them are graphs, because we are interested in graphs. These are pure graphs, which means that they are graphs essentially with no labels, neither on the arcs nor on the nodes. They are graphs either directed or undirected. Some of them are web crawls. We have a crawler of our own. So we used it. Now we are not using it anymore, but we used it for some time, and we did some small crawls. As you see, these graphs are about 1 million of pages at most. And then there are some larger graphs like these ones that are a few tens of millions of pages. And actually, there is even, at the very end, there are even some big graphs, like in the order of 100 million of nodes. And then we also have, you can see them here, some social graphs, like, I don't know, the Enron graph. You know what the Enron graph is? You know what Enron was or is? It was a big American company that was involved in a big scandal at some point. And actually, during the trial, all the emails that were exchanged by the CEO and the other directors of the company were collected. And so now we know who exchanged a mail to whom, and this is a big graph, and it's called rather big graph, and it's called the Enron graph. And then there is the Amazon graph, the LiveJournal graph. LiveJournal is a social network. Orkut graph. Orkut is another social network. These are the Hollywood graph, the co-actorship graphs. So its nodes are actors, and there is a link between two actors if and only if they co-starred in a movie. I collected them from the Internet Movie Database. These are the DBLP graphs that are scientific, so the nodes are scientific authors, and there is a link between two nodes if they wrote a paper together, blah, blah. And what else? These are Facebook graph. Actually, we are not giving away. Some of these graphs you have. So if you click on, let's say, I don't know, Hollywood 2011, so you see some of the characteristics of the graph, like how many nodes, arcs, blah, blah, the in-degree distribution, the out-degree distribution, the distance probability mass function, the size of connected components, blah, blah. But what's more interesting for you is that you can download the graph itself. For most of the data sets, for the ones for which we don't have legal problems, we give away the actual graph, and you can download it. The format of this graph is web graph, which is something that I'm going to tell you this afternoon. For some graphs, we cannot give away the actual graph. Like, for example, these Facebook snapshots are not, we don't own them. We don't have the legal permission to give them away. But still, you can click on it and, for example, let me see. OK, so Facebook current, which is the largest snapshot of Facebook we have. So we can give away some data, because we asked Facebook permission to do that. So you can have the degree distribution. The degree distribution, by the way, is the distribution on the number of friends a person has. So this means that this is the absolute frequency. So it means that about 10 to the 7 pairs of Facebook users have 9 friends. Sorry, about 10 to the 7 users have 9 friends. Most of them. So most people on Facebook have less than 10 friends. This is the distance probability function, blah, blah, but we don't give away the graph in this case, because we can't. So this is something you may be interested in. There are lots of data. And then there is software here. Now, we give away a lot of software under different packages. All our software is written in Java, and it's licensed under GPL or LGPL. So it's free for you to download and to use and to modify. And you are welcome to contribute packages if you want. Our software is basically contained in some libraries. One of them is called the Law Library. And in the Law Library, if you look at it, you can browse the API. Is anybody programming in Java here? Oh, only a few of you. But anyway, you can learn, right? So in particular, there is a package here called Rank that contains implementations for PageRank in particular. So various methods to compute PageRank, like using the power method, Jacobi, Gauss-Seidel. All these classes allow you to compute PageRank, compute its derivatives, evaluate it, do the things that I explained yesterday. You can choose the damping factor, you can choose the preference vector, blah, blah. And by the way, there is another package here that is called stat that contains the implementation of Kendall-Tau. You remember yesterday I told you about Kendall-Tau. Kendall-Tau apparently is easy, but actually its naive implementation is quadratic in the number of nodes, which for graphs of that size is unbearable. So we actually have an implementation that is n log n. It's based on an algorithm called the Knight's algorithm. And as far as we know, we are the only ones who are distributing the Knight's implementation implemented in a reasonable way. So this is Kendall-Tau. So this was the low package. And then there are many other packages. Some of them are actually part of separate downloads in the sense that they are individual contributions. They are not written by the whole lab, but only by some of its members. In particular, I am one of the authors of WebGraph, and MG4J. Web graph is something that I will tell you this afternoon, actually, and it's a system used to compress big graphs and to use big graphs. You can go to the specific web graph page, download it, look at the APIs, blah, blah. And then there is MG4J. MG4J is an information retrieval search engine. So you can use it to make queries to large textual data sets. It's similar in nature to managing gigabytes. Has anybody heard about MG, managing gigabytes? Well, apart from you, of course. Well, anyway, it was born as a sort of revival of MG. Actually, now it's quite larger. It's similar to Lucene, if you ever heard about it. But it's better than Lucene. Of course, I am one of the authors, so what can I tell you? What else? So there is another nice package that is called FastUtil. It was not written by me, but by Sebastiano Vigna. It's really nice in general. It's a set of utilities to have very efficient memory and time-efficient implementations of primitive types collections. Like you have set of integers, set of doubles, maps from integers to doubles and whatever, but implemented in a very efficient, time and space efficient way. Very efficient. And what else? We use FastUtil at every moment because we are dealing with very large data sets. So we need very fast implementations of everything and very efficient implementation of everything. That's why we started building up our software collection exactly from FastUtil. And then there is Sux4J. Sux4J is very interesting, and it's a collection of things that are needed if you want to deal with many strings. You have many strings and you want to crunch them in some way, then you should think of using Sux4J. And actually, the next topic that I'm going to touch with you this morning is minimal perfect hash, and it's something that is contained in this library. What more? Well, a lot of things. I invite you to go to our website, look around to see if there is something that matches your flavors, your tastes, your needs. And in case, download it. There are also some satellite projects that are contributed by other people or by ourselves. For example, there is some software for weighted PageRank. Some of you at some point asked me about weighted PageRank. So there is a package implemented, the weighted version of PageRank there. There are classes for approximate triangle counting, which is going to be a topic that I'm touching, I don't remember, today or tomorrow. And there are some classics about voting elections in social networks related to a paper we wrote some time ago. Anyway, you are welcome to try to look at our website and see if there is something that is interesting for you. So let me go to the second lesson. That is about large dictionaries. So, okay, the topic of this class is actually no graphs anymore. So we are going to use graphs, but only as a tool. Actually, this is more related to dictionaries. But there is some relation with graphs that I will tell you about. So the overall problem is the following. You have a set of URLs, or a set of strings, if you prefer, and you want to number them. You want to assign a number to them. Why would you want to do this stupid thing? Well, one reason is the following. The web graph, you know what it is. So you have a crawler, you start downloading pages, and you end up with all those pages. So you have, suppose you have downloaded 100 million of pages, then you have 100 millions of files on your hard disk, and each of them contains a web page. So you have a.html, b.html, blah, blah. 100 millions of times. Each of them contains a web page that you downloaded from the web. Now from this big mess, you want to obtain the graph. For example, to compute PageRank. How would you do that? How would you do that? Tell me. Oh, well, you know. So the problem is you have to take these HTML and extract links from them. This is easy. But once you have the links, how do you actually build the graph? Remember that at the end, in the graph, you don't want to have URLs. You want to have numbers. Like these are nodes, number 0, 1, 2, 3, 4, 5, 6. And when you parse one of these pages and you find a link there, you want to know what number this link corresponds to. If it's number 1000 or 7 or 12. So as a first step to build this graph, you have to take the names, the URLs, corresponding to these files, and you have to assign them a number, so that after that, you can build the actual graph. Do you see the problem? Okay. So what you need is a rapid and fast and efficient way to map URLs into numbers. If you have n URLs, you want to map them into the numbers between 0 and n-1. So you need a map from the left-hand side to the right-hand side. The very same problem appears many times. Even if you are building, for example, a search engine and you want to map strings to numbers, because of course they don't want to deal with numbers, they want to deal with strings. So in that case, on the left-hand side, you will have the strings corresponding to the vocabulary of the pages you have downloaded, and on the right-hand side, you have numbers. Now, actually, the numbering is more or less arbitrary. There is no specific reason to assign a particular number to a page. The only important thing is that you map n pages to n numbers. But for some reasons that it will turn out that it's useful, it's more useful that the numbering is lexicographic. So on the left-hand side, you have the URLs you have collected in lexicographic order, and on the right-hand side, you have the numbers from 0 to n-1. As I told you, this is used to build the graph. Now, what is the obvious way to do the job? The most obvious way to do the job is keeping the URLs in an array. So you keep an array of strings that are the URLs, and every time you want to look for some specific URL, you will search in the array. So let's try to do some computation. I did it for you. Suppose you have 1 billion of nodes. Now, if you have 1 billion of nodes, which is not too much, 1 giganodes, first of all, the space required to keep the strings is about, I wrote 300 giga, assuming that each string on the average is 300 characters. Probably it's more than that, because nowadays URLs tend to be very long. But 300 gigabytes of memory, well, of course, if you have a large enough machine, you can have 300 gigabytes of RAM, but it's not, it's not going to be cheap. And even the binary search will take about 30 comparisons. So the time is not going to be negligible, because every time you look for a string, you will have to do 30 string comparisons. It's a lot. How many of you have some algorithmic background or computer science background? Okay. Some of you did like. So this class today is more algorithmic than yesterday. Hope you like it. Or you don't dislike it at least. So the problem is trying to solve the very same problem without keeping the strings in memory. This is the problem restated in another way. You want to map x to f of x, where x and f of x are specified in this table, without keeping the x's in memory. And you want to do that quickly. So given x, you want to compute f of x very quickly. You don't actually care about the construction time. So it can take some time to build this data structure, whatever it is, because you will do it only once. Once you have the data structure, you use it, you query it. So construction time is not a problem, provided that it's reasonable. Like it cannot take 1 century to build the data structure. And nicely enough, we don't need an inverse function. So we don't need a way to map the number into the string, which is a completely different problem. We only need to map x into f of x. And I will tell you a recipe to do that. But before this, I will need to be sure that we all agree about what a hash function is. Who of you know already what a hash function is? Okay, good, many. So the general problem is the following. You have a universe of things that I will call omega. Omega in our case is going to be a set of strings. So you have a universe omega that can be even infinite. And you have an integer m. And an m bucket hash function is a function that maps every element of omega in the set of strings of numbers between 0 and n-1. This is called an m bucket hash function. And usually, when one thinks of a hash function, he has 2 things in mind. First of all, it is something that is very easy to compute, very quick to compute. And it must be as injective as possible. This sentence is not very mathematical. I will try to be more precise later. Of course, keep in mind that it cannot really be injective. For example, the trivial reason for which it cannot be usually injective is that omega is much larger than m. So, of course, as soon as omega is larger than m, you cannot hope to find an injective function. When I say it is as injective as possible, what I have in mind is that there is some set S, there is a subset of omega, and we want H to be injective on S. So actually, on the set of all strings, there will be a subset of strings on which I am interested in, and I would like the H to be injective at least on that set. Of course, this is possible only if the set is small, because again, if the set is larger than n, there is no way to find an injective function. Now, if H is injective on S, we say that H is perfect for S. So a hash function is perfect on a subset if it's injective on that subset. I don't know why they decided to call it perfect and not injective, which is the right way to call it. You're following me? Okay. So, in particular, if the set is exactly equal to M, we say that H is minimal perfect. If the size of S is exactly M, it means that H on that set is bijective. So a perfect hash function is injective. A hash function is perfect on S if it's injective on S. And if moreover it is bijective, we say that it's minimal perfect. So minimal means surjective. Now, usually, it is impossible to obtain a minimal perfect hash function simply because you don't know S beforehand. So if you don't know S beforehand, which happens in most of the cases, there is no way to find a minimal perfect hash. But in our case, we know S. S is the set of strings that appear on the left-hand side of our table. So our purpose is to build a minimal perfect hash function for that specific set of strings. And I will tell you how to do that. Okay? So at the very end, the situation will be the following. Here is the set of all possible URLs. Or let me say the set of all possible strings. This is our universe. Among these strings, there is a small subset. This set is infinite, right? Among these strings, there is a small subset. There is the set of URLs we have crawled. To do is the following. So, well, it's easier to look at there. Can you read when I write here? Sort of. So one way is the following. You take an extra vector of bits, we call it R, And the vector R contains zeros and ones, and it contains a 1 every time H maps some string of S into I, into that specific index. So you look at all the strings in S, and you will see where they end up in the set 0, m minus 1. Notice that H is injective. So if there is a string that maps to number 3, there is only one string. Either there is one string or there is none. But there cannot be two strings of S mapping in the same index because H is perfect. H is not minimal, but it's perfect. So at the end, the vector R, how many elements of the vector R will be ones? N. Exactly as many as the cardinality of S. So R will be a long vector of zeros that will contain exactly cardinality of S once. The cardinality of S in this lesson is going to be N, always. N like Naples, N. So what we do afterwards is we define g of x as following. G of x is the number of ones before R of h of x. So we map x using h of x, and it will end in some index. Then we count how many ones appear before that index. It's like compacting the array. Are you following me? Okay. So counting the number of ones in a vector of bits is before a given one is called the ranking problem. So the bit vector ranking problem is the following. Given a vector of bits, zeros and one, and given a specific position, count how many ones there are before that position. This ranking problem has a sort of dual that is called the selection problem. That is, given a vector of bits, tell me the position of the 7th one. This is called the selection problem. Now, there are good data structures to solve these two problems together. These data structures are called rank select data structures. So a rank select data structure is a data structure that that is built on a bit vector and that allows you to solve these two problems. To determine how many ones appear in the vector before a given position, or to determine the position of a given one. Tell me what is the position of the 8th one in the vector. And you can see in the literature that it is possible to build rank select data structures that work in constant time. In constant time, it means that the time is going to be independent from the length of the vector, and that use only small o of the length of the big vector extra bits. So essentially, if I give you a perfect hash function, you can turn it into a minimal perfect hash function by using only small o of m bits, where m is the range of the original function, and in constant time. Of course, I am not telling you how those rank select data structures work, but you can do that. Okay, so have you got it? Following me? Bon, good. Now, another problem that you may find interesting, this is another ingredient that you may use afterwards, is the problem of signature. This is interesting because many people don't actually understand this problem. So, suppose that I have already built a minimal perfect hash function. So a function that on the set S of URLs that I have crawled is bijective. And what happens if you try to apply H to an element that is not part of S? What do you think it happens? Nothing special. H will answer a number. Of course, what you should say is that you will apply H only to the set S. But the problem is that sometimes you don't know what the set S is. Let me give you a specific example. So recall the problem I said before. So you have the pages you have crawled, and each of them corresponds to a given URLs, and we want to build a map that maps these URLs to numbers. Now, in these pages, there will be many anchors, many links appearing. Some of them will be part of your crawl, but some of them will not, because you didn't crawl the whole web. So sometimes you will find links here that don't appear among the pages you have crawled. You must be very careful, because those links, you cannot apply H to those links. Otherwise, you will think that there is a link to a page that does not exist. Let me give you are you following me, or you want an example, a more specific example? You want an example? Okay. So suppose that here there is a link towards my home page. HTTP Boldi DSI Unimi. It. Okay? So this page contains a link towards my home page. But suppose that my home page was not crawled. So first of all, you take all the URLs that were crawled and you build the minimal perfect hash function in the way that I'm going to tell you. So you're going to have a map H that goes from the set S of URLs you have crawled into the set 0 n minus 1, where n is the cardinality of S. And after that, you are trying to build a graph. So this is a certain URL. Let us assume that it corresponds to page number 35. So it will be node 35 in the graph. And now we want to know which nodes it points to. So we take all the links that appear in the page, we parse the page, and for each of those links, we will look at the URL and we will apply H. Of course, we will apply H also to this string here. But this string is not part of S. So H will answer some number, some essentially random number, because H was not thought to be applied to this specific string. This string is not part of S. But we don't know when we parse the page, because we don't have the URLs in S anymore. So we try to apply H to this string here, and we get a number, let's say 71. This is essentially a random number, but we don't know. And so we think that there is a link from 35 to 71. But 71 is not my home page. It's another page that was crawled. So we are building the graph in the wrong way. You're following me? Okay. So in this case, before trying to apply H, you must have a way to know that if this string is part of your crawl or not, which is a completely different problem and not taken into consideration by H. You must have a dictionary to know if this was part of the crawl or not. And only if it was part of the crawl you apply H. Otherwise, you discard it. Now, there is actually a way to do the job by doing what is called a signature of the map. A signature of the map is a way to transform a minimal perfect hash into something else in such a way that if you try to apply it to an element that was not part of S, it will answer -1, which means this was not part of my domain. It's like an error value. And one way to do that is the following. You take a minimal perfect hash, and you want to avoid that if you try to apply H to an element that was not part of S, it returns a reasonable value. What you can do is you can compute for every element of S some signature like CRC, some signature value, so some small value that is a signature of the string, and then you store those CRC in an array. In particular, so what I'm doing here is for every element of S on which the function H was built, I compute a signature, which is a long integer. Okay? So I have a long integer for every element of S, and then I fill an array with those signatures. So let's say that here I have a certain URL U. URL U is mapped onto a certain index I, and then at position I of the array S, I will store the signature of the string U. then what I do, so you keep this signature array along with the hash function. And then what you do is the following. Whenever somebody tells you, asks you, please compute h of x, you do the following. You compute h of x, and then you will check that in the signature array, in position h of x, there is the signature of x. Of course, if x was part of S, if x was part of the original set, the answer will be yes. If x was not part of S, the answer may be yes or not or no, depending on whether by chance the CRC of this element is equal to sigma of x or not, but most usually it will not be equal. So there is a high probability that these two elements will not be equal. So if they are equal, you return h of x. If they are not equal, you return -1. And here you can play on how long you take the CRCs. If you take long CRCs, the probability that by chance they are equal if they are not will be negligible. You got it? So this is a way to sign a map. Signing a map means to be sure, or to be almost sure, that if you try to apply the map to something that was not part of its domain, you will get a -1 and not a number that may fool you. And by the way, we are in our libraries, we have signatures classes. So you can build an MPH, a minimal perfect hash, and after that you can sign it if you want, in case you need it, of course. Sometimes you don't need it. I mean, depending on the actual application, you may or may not need to sign your function. Now, I am almost going to tell you how to build a minimal perfect hash. I have to stop at 12:30, right? Okay. So first, before starting, I will give you a brief overview of string hashing. So the general situation is the following now. You have a string of a certain length. Let's say a string of length up to W. And you want to compute a hash and a m bucket hash on this function, on this string. The way one usually does this is the following. Beforehand, one draws W weights at random between 0 and then -1. And then to compute the hash of a string, let's say that the string you want to compute the hash is Nino, okay? So it's N-I-N-O. So every character corresponds to a number. Then you take the number that corresponds to this specific character. In this case, it's 110, 105, 110, 111. You multiply it by the corresponding weight, and you sum all of them modulo m. So you do this computation. 110 times 3 plus 105 plus times 12 plus blah, blah, modulo m. And you get a number that is something between 0 and n-1. This is called the universal hashing of strings, and it depends on this weight vector. This weight vector is computed once and forever. So if you want to generate a random hash, you compute these weights and you keep them on the side. And with this, you will hash strings into numbers between 0 and n-1. So this was important because now I will tell you one of the parts of the recipe is generate a hash on strings. When I say this, I mean generate a set of weights. If you need 2 hashes, you need 2 array of weights. Okay, so let us go to the MWHC array. The first part is, so we start with the table. Okay, we start with the good table. On the left-hand side, we have the strings. We have the array of strings. And on the right-hand side, we have the numbers between 0 and n-1. We start by fixing some m, some integer m that is larger than n. I will tell you after how to choose m. And then we choose uniformly at random 2 hash functions, h1, h2, with m buckets. By this I mean you generate two arrays of weights. And now so you have the strings, you have the numbers into which you want to map those strings, and you have the two hash functions you have generated at random. Each of them will map each of these strings into a number between 0 and then -1. Suppose, for example, that h1 maps this string into the number 231, and the same string is mapped by h2 into the number 3443, and so on. What you do now? You build a graph. You like it, right? You build a graph. And you build a graph as follows. The graph has vertices, the number between 0 and then -1, and you put an edge for every string. And the edge connects h1 of x to h2 of x. So for example, you will suppose that m is, I don't know, 10,000 in this example. So you will have 10,000 of nodes, the numbers between 0 and 9999. And you will put an edge between 231 and 3443. You will put an edge between 32 and 5534, and so on. How many edges are you going to have? You say n? Actually not. It depends. Because why not? Why not always? There can be collisions. So it may happen that for two different strings, h1 and h2 are equal. So h1 of x is equal to h2 of x. Sorry, h1 of x is equal to h1 of y, and h2 of x is equal to h2 of y, or the other way around. Or another thing may happen. It may happen that for a given string, h1 of x and h2 of x coincide. So there is a self loop, and you don't want self loops. If this happens, you throw away h1 and h2 and generate two more hash functions. So you repeat the process until there are exactly n edges, and all of them are non-loops. And actually, you want more. You want the graph to be acyclic. So every time you generate h1 and h2, and you have to check three things: that there are no collisions, that there are no loops, and that the resulting graph is acyclic. If any of these three things happen, you throw away h1 and h2, generate two new weight arrays, and repeat. Well, is there any chance that you succeed? Actually, so. If m is large enough, if m is larger than 1.75 n, with a high probability, you will get a graph that is acyclic. Actually, you don't. Only 2 attempts are needed on the average, so it's not much. Okay, so you do that, and you end up with this magic graph. And now you look at the graph. So now h1 and h2 have this nice property of corresponding to an acyclic graph with exactly n edges, one for every string. And you transform this graph into a set of equations, of Diophantine equations. You have one equation for every string, and the equation is the one that you see there. So the equation, for example, the equation corresponding to this string is x231 plus x3443 modulo m equals 0. You have a set of equations. Now, if you look at this set of equations, suppose that you can solve it. It means that you can assign to every node of your graph a number in such a way that if you look at an edge and you sum the two numbers corresponding to the two nodes on which the edge is incident, modulo m, you get exactly what you want. So you get exactly the number that the string should correspond to. So the recipe would be the following. Tell me what is the number corresponding to Pippo, Pluto, xy. Then you apply h1 and h2 to that string. You get the two nodes on which the edge is incident. You get the two x's, the two values corresponding to the two nodes. You sum them, do modulo m, and you are done. You following me? So the only problem is solving this system. Now, the fact that the graph is acyclic guarantees that you can solve this system. And I will tell you how. So actually, this is a theorem, by the way. So if the graph is acyclic, this system admits a solution. But I will tell you how. The reason is that if the graph is acyclic, you can reorder the equations in such a way that in every equation, at least one of the two variables never appeared before. In this very stupid example, a reordering would be like this. So you see, in every equation, there is at least one of the two variables that never appeared before. Okay, in the first equation, this is trivial. For the second equation, so no, I have to reorder them. So these are the equations reordered. So for the first equation, it's obvious. For the second equation, well, this variable already appeared, but this variable is new. And in this equation, this variable already appeared, but this one is new. If you reorder the equations exactly in this way, it's easy to find a solution for the system. Because, okay, for the first equation, you can do whatever you want. For example, you can assign 0 to both variables. For the second equation, okay, one variable has already been assigned, but the other one is free. So you can assign it in such a way that the equation is true. And you go on like this. You following me? So it's easy. Well, almost easy. Actually, it's easy. And this new variable is called the hinge of the equation. So the hinge of the equation is the free variable. If there are two, you choose one of the two. So for example, the hinge of this equation is x32. The hinge of this equation is x5534. I need this terminology because later I will use it again. So the point is, you have this system of equations, and you have a way to reorder it in such a way that every equation has a hinge. And then you assign the values to hinges in such a way that the system is solved. And so, at the very end, what you need is only h1, h2. These are just two arrays of weights, as long as the longest URL you have. So they are very small. And anyway, independent on the size of S. They only depend on the size of the strings. And then you need to keep the array X. How big is the array X? As I told you, you can choose the array X in such a way that is 1.75 times the number of strings. So you just need 1.75 times the number of strings integers, which is much less than the strings, right? So more or less, you need about 2n integers, which means 2n log n bits, plus the two weight vectors that count nothing. 2n log n bits instead of all the strings. Okay, so it's almost nothing. 2n log n bits, if you have 1 million of strings, is 2 million times something bits, which is nothing. You can store it in memory. Observe that we will not be able to compute the inverse of f because we are throwing the strings away. And actually, we did something stronger than building a minimal perfect hash, in the sense that we did not build any minimal perfect hash. We actually chose to which integer we have chosen exactly which integer each string is mapped to, which is more than any minimal perfect hash. If I just care about any minimal perfect hash, probably I can do better. But here I can even choose the order of the strings. Okay, so now what I just explained is not the real MWHC graph algorithm, because you can repeat the same construction not using graphs but using hypergraphs. Who knows what a hypergraph is? Only you. So a hypergraph is a generalization of a graph where edges do not touch only two nodes but many nodes. So a K hypergraph, let me say what a 3 hypergraph is. So a 3 hypergraph, they are hard to to be drawn, but a 3 hypergraph is something like this. It's something where the edges are not, you cannot draw them as lines, but you draw them as triangles. Because every edge touches 3 nodes. Something like this. Of course, you can repeat exactly the same construction, but instead of building a graph, you will build a hypergraph, where there is a hyperedge for every string. Instead of using 2 hash functions, you will have 3 hash functions, h1, h2, h3. And you can essentially have the same notion of acyclicity. It's a little bit harder to define, but it's more or less the same idea. And you will have equations that will contain 3 variables each. And you can do it on a 4 hypergraph, on a 5 hypergraph. So you can repeat the same construction. What is the advantage? The advantage is that if you take a 3 hypergraph, the probability that it's acyclic will be larger. So it will take, The point is that you will need less nodes to have an acyclic graph. And you can actually prove that, for example, for a 3 hypergraph, you don't need 1.75 n nodes to have high probability not to have cycles, but you only need 1.21. And for some magic reason, 3 is the best. In the sense that if you try with a 4 hypergraph or with a 5 hypergraph or more, you get worse. So the best is using a 3 hypergraph. And with a 3 hypergraph, you get 1.21 n log n bits to store a minimal order preserving hash function. Okay, you like this construction? I find it magic. I find it magic. Actually, they didn't realize when they wrote the paper, but this very same construction can be used to map strings into anything. So suppose that instead of mapping strings into the numbers between 0 and n-1, you want to map, let's say, the strings of S into some array of bits. Let's say into some array of cardinality of psi bits. You want to map Pippo blah blah into into this bit sequence, and this for every string. Where these are chosen arbitrarily. The only thing you need is that they can even be equal to one another. You chose them and you apply exactly the same construction. But this time you take as integers these values. So actually you can use the same idea to map the set S into every set. And you need 1.21 n log cardinality of psi bits. Because there, so the element that appears here is the length in bits of every element of the array X. In the previous construction, it was log n bits. In this construction, it is log cardinality of psi bits, but it's the same.